Hi, I'm Mark DeLuzio, and we're here to do a little primer on what we call standard work. Standard work, it's a term that's used by a lot of different people to mean a lot of different things. When you talk to somebody who's been trained by the originators of the Toyota production system, like I have, and like people at Lean Horizons have, you know that standard work means something very specific, and it is probably not the best, you know, term that was used because it seems as if it's a very generic term. I'm going to talk about what real standard work is. So when you talk to somebody like myself who's been trained by the originators at Toyota, you'll know exactly what we're talking about when we do say standard work. One thing to remember that there can be no Kaizen where there's no standard. That comes right from Taiichi Ohno, who was the father of the Toyota production system. So let's move on and talk about what this is all about. I want to start first with this chart. I always start with this chart. As we think about a lean transformation, obviously we want to make a lot of money. There's nothing wrong with making profits, right? Satisfying our shareholders, or if you're private, your owners, got all that, right? But this trilogy that I created, it's called the Lean Trilogy, we need to satisfy the objectives of these three major stakeholders: employees, customers, and shareholders. Now, I do understand that there are other stakeholders to consider. There's the environment, there's the community, society, all that good stuff. There's the government, okay? There's our supply base. However, these three are what I focus on first. Uh, when you look at this and you say to yourself, well, geez, if I don't take care of my employees, how are they going to take care of my customers? And if I fail on the customer front, how is that going to translate into favorable results from shareholders? Now, we may all think we know what employees and customers want, and even we may think we know what shareholders want, but do we really? Okay. Have we asked them? How do we understand that? Do we do surveys? Do we talk to them? Okay. So keep that in mind. This trilogy means that this cannot be a zero sum game. It cannot be one group wins over another. Everybody has to win. So think about that and remember that lean is not about equipment or products or processes or anything of the like. It's about people who drive all those other things. And that's what this is all about. Okay. Okay. Today's agenda. This is kind of a condensed version from my larger standard work presentation, but I'm going to talk about a couple of different things. I'm going to talk about an introduction as to what standard work is. I'm going to talk about the three elements of standard work, which are crucial in order for you to call it standard work. These elements have to be present. Cycle time concepts, and there's a lot of confusion over that, and documentation. I'll touch briefly on the documentation because that is a big part of standard work. Okay. Okay. First off, let's talk about standard work. If you've seen my videos before, you'll see that standard work is one of the three things on the foundation of the Toyota production system. And my sensei Chihiro Nakao said, if you don't understand standard work, you don't understand the Toyota production system. Okay. Now, what does it mean to understand? Nakao and our other Japanese senseis like Mr. Iwata and what have you, they all couldn't understand why Americans in particular would say they get it, they understand, but couldn't do it. And I'll tell you a case study for me. Back in the 90s, I had Nakao come in to my plant, and I was running operations at the time in the Asian business team. Matter of fact, Nakao and I worked on the first 3P line in the United States, which was kind of an honor for me to be part of that. Anyway, And we did that for Hino Motors, which is part of Toyota. So we worked with Hino engineers as well. But anyway, Nikao came in and I said, Nikao-san, we need to work this week on, I don't know what it was, SMED and TPM. Nikao said, no, Deluzio-san, we need to work on standard work. Ah, come on, Nikao-san, I know standard work. I could do time observation studies by myself. I don't even need a partner. I know how to process capacity sheets together. I can do operator loading charts. I could do combination sheets. I could do everything in standard work. I know standard work. I know how to calculate takt time, right? Deluzio-san, come with me. We went down to one of my cells and we looked at the standard worksheet, which is one of the 5 documents you'll see later. He said to me, how many people are on your standard worksheet? And I said, 5. How many people in your cell? I looked and counted, and shamelessly I said, 8. Deluzio-san, you do not understand standard work. Okay. And again, be careful of people who say they understand, but they can't do it. All right. Intellectually understand how to hit a golf ball and really hitting a golf ball correctly are 2 different things. All right. Lesson learned from me. Again, when you're younger, you think you know it all, right? And the older you get, I think you find out how much you don't know. Okay. I want you to think about this. Standard work is not a noun, it's a verb. It's not something that you did, it's something that you do. You work to standard work, you work to this. It's an ongoing, continual endeavor. Standard work is not a project that gets completed and checked off. It's how we run our operations. And I'd like to give you an example of what I mean, and I like to use outside analogies. If you're setting up a manufacturing cell, or let's say a flow in an office, and again, one of the requirements for standard work is it needs to be a repetitive process. Okay, uh, and you look at people and process layout, instructions, and what I call rhythm. I'll get to that in a minute. People, manufacturing, of course, your production workers, your operators. In the office, you have your office staff. And in an orchestra, you have your musicians. Now, what about the process layout? We have a cell design for manufacturing. We have an office flow in terms of how we're going to flow work. And in a orchestra, you have all the instruments laid out in their appropriate sections, right? Percussion and woodwind and all that. Okay. Now, let me stick with the orchestra for a minute. If I said to you, hey, we got this orchestra all laid out exactly the way we want it, but we're not going to give them any sheet music. How do you think that orchestra is going to sound? Okay. Not good at all, right? How many times have we set up ourselves, whether it be in the office or in manufacturing, and we didn't provide the sheet music, which are the documentation of standard work? And I'll go into that documentation a little bit later. We do it all the time. And then we say, well, geez, I don't understand how come that cell can't get their product out? And we have all kinds of takt time violations and everything else, which I will talk about. Now, let's talk about the conductor. He keeps the beat. Well, takt time is an integral part of standard work, okay? And it will be incorporated into all the things that we do. Takt time is a German word meaning beat. I'll get into that in a little bit. So, how would this orchestra sound without that beat, without that conductor? Okay. How would this orchestra sound without the sheet music? You got variation problems, you got quality problems. This could be a major reason why, because you set up the orchestra, but you didn't give them the conductor and you didn't give them the sheet music. Okay. So keep that analogy in mind as you go through. Okay. What are the 3 elements of standard work? Well, takt time I already mentioned. Takt time is the beat, it's the rhythm, okay, of how often we have to manufacture a part or deliver a service or a document, whatever it might be. The work sequence happens to be those steps that an operator is going to take that has to be in within takt time. Okay. So maybe it's assembling a part in loading and unloading and gauging or whatever it may be, right? And standard work in process is the amount of inventory needed to keep your operators flowing. So in other words, if I have a machine that has a piece of work in process in it and it allows me to walk away to the next process, that piece is called standard work in process. I'll get into that a little bit more. These are the three elements of standard work. Now, when people say, oh, yeah, we got standard work, and they refer to anything and everything that's written and documented as standard work. Well, that is not in context of what we believe standard work is. Okay. So, takt time. Okay. Right out of Toyota, takt time is the pace of sales in the marketplace. Takt time is based on customer demand. I'll show you the calculation in a minute. Okay. And don't confuse takt time with any other form of cycle time or lead time. Takt time is written in red on purpose. I'll explain that in a minute. Okay. But how often should a part or service be produced based on the rate of demand to meet your customer requirements? Okay. Now, the history is it's a German word. The German aircraft firms moved fuselages ahead to workstation at intervals determined by what they called takt time. And Mitsubishi, who made the Junker aircraft in World War II for Germany, okay, coined this, and Toyota incorporated it into the Toyota production system after the war. Takt time was written in red because Taiichi Ohno was sick and tired of people confusing takt time with cycle time. Okay. So to honor Ono and Nikao and Iwata, I always write takt time in red. Whether I draw the line, if I'm on a whiteboard, I'll look for a red marker. It's out of respect, but it's also the discipline that's instilled in us in terms of how to think about takt time so that nobody gets confused. Okay. Now look at the metronome on the left. That's kind of like keeping the beat of an orchestra, right? That's what takt time is. What's that takt image in your company? When you walk in, can you feel a takt image, a beat, a rhythm? Can you kind of feel it? Can you hear it? Can you smell it? Can you see it? Right? That's what we're looking for in terms of takt time. How do we calculate it? Pretty simple. You take your available working time divided by your demand for that area. So this could be for a cell, for a work line, for a cell, for a department. You know, it's got to be relative to the area itself. So if I have 27,000 seconds available, and I take out breaks because that's not productive time or cleanup time or whatever, and divide by 350 units, my takt time is 77 seconds. Okay. So that's how we calculate. It's a pretty simple calculation, right? Now, what do we use this for? I could use it for operators required. I take my takt time divided by the cycle time of the operator. That's all of the seconds it takes to make one product. So let's just say my takt time happens to be 100 seconds, and I have 900 seconds worth of cycle time. When I divide those out, it means I need 9 operators. Now, no one of those 9 operators can have work more than 100 seconds. If I have one at 110 and everybody else below takt time, guess what? My drop off rate in that cell is 110 seconds. So I'm going to miss my deliveries because I am not producing in accordance to takt time, in this case, 100 seconds. Okay. My standard working process. Well, if I have, let's say, a curing oven or an outside process that goes to, let's say, heat treat, I take the lead time divided by takt time. That's how much inventory I need to have in the cell for me to continue to work into a one piece flow environment. Okay. And my processing capacity is my machine time and my load unload time. Okay. That has to be lower than takt time. Otherwise, I'm going to have a bottleneck with that piece of equipment. All right. Again, if my takt time's 100 seconds and my machine cycle time plus the load unload time happens to be 120, I'm going to miss by 20 seconds every time I have a part pass through that machine. And that adds up at the end of the day. Okay. So not only do our operators have to be in concert of takt time, so does our equipment. All right. And all this gets documented on a standard work combination sheet, which we'll show you in a bit. Okay. Work sequence. This is this represents the steps required for an operator to complete one cycle of work for one part. Okay. Remember, the work sequence must be equal to or less than takt time. If it's greater, you got yourself a bottleneck. So let's just take the three people in this cell. They're probably doing unload, load, assembly, gauging, whatever it is, right? And notice how with the U-shaped cell, and this is maybe a discussion for another day when we talk about cell design, instead of having operators operate linearly from, let's say, operator 1, 2, and 3, and having great walk time going back, we go across the cell. Maybe this isn't very representative because this cell would be a lot more narrower than what maybe is being shown. To reduce walk time, you go across the cell. So this second operator here might go from 3 to 4 to 8 to 9 and back to 3 again. That's one cycle, one sequence. That sequence, the amount of time it takes that operator to do that, including walking time, which we want to reduce as much as possible, okay, is in fact the total cycle time for that operator. And it's got to be under takt time. Same with the other operators as well. Okay. By the way, chairs in a cell, I am definitely against them. I'm not going to take a lot of time talking about it now, but I will tell you that if you go to lean911.com, that's my podcast, or it's on Apple Podcasts or Spotify or whatever, or YouTube, I have an episode on chairs in a cell. Go listen to that and get my perspective on what I mean when I say I don't allow chairs in a cell. And there's some very good reasons why, and you'll find that in that podcast. Okay. So again, I want to make sure that my operators are within the context of takt time. Okay. That's my work sequence. Now here's a way to think about it. One of the things the cow told me was, Deluzio son, how can you hit takt time when you have your operators doing all these other jobs that aren't spelled out in their work sequence in the context of standard work? You've got your operator leaving the cell to go get tooling and go get materials and deliver parts to finished goods. Well, that's not part of their standard work. He said, Deluzio son, operators should operate. That's all they should do. Now, the analogy I like to make is race car driving. The driver is the operator, the track is the work sequence. Our job is to keep that driver on the track as long as possible until they win the race, right? Well, maybe we want to save on productivity and get rid of some pit crew people, and we'll have the driver change his own tires. Well, that's not going to work, right? In the old traditional cost accounting, I was taught that indirect operators are waste and direct operators are not waste. Well, guess what? How would you like to get rid of your pit crew just in the context of saving on cost? If you're a race car driver, guess what? You're going to lose the race. Now, both of those indirect and direct operators have waste within their cycles. Just because the operator is putting a product together doesn't mean that that direct operator doesn't have waste. And same goes for the indirect operator. So the whole idea here is to say to ourselves, look, we do want to take as much waste out as possible, but the indirect operator, in this case, I'm calling that person a water spider, or the pit crew as it relates to the driver, the race car driver, is to keep that operator or keep that driver on their track. or their work sequence. Okay. That's what we really want to do here. So these water spiders are crucial of keeping our operators operating. If you ever have anybody challenge you on that, go right back to NASCAR and talk about this pit crew. Okay. Okay. Standard working process. All right. It's the amount of inventory needed to keep the operator flowing. So what I don't want to do is have the operator load a part into a machine, hit the green button, and stand there and watch it. What they should do is unload the part that's been there already, load the other part, hit the green button, and move on to the next operation with that part. You know, you're not going to stand there and watch your clothes dryer wash clothes. You're going to walk away from that and go do something else, right? So we want to think about where the opportunities are. Now, a lot of businesses have curing ovens, they have burn-in times, and all that. By the way, I would challenge these burn-in times really big time. So many times they're divisible by 8 hours. Certainly doesn't understand like it doesn't sound like a engineer standard to me. I once challenged a 48-hour cure time, and when the engineers got done, it turned out to be 20 minutes. All right, think about that. So challenge everything and don't accept these times as being gospel, and especially when they're divisible by 4 or 8 hours. So you're going to see that. Oh yeah, we have to burn that in for 8 hours. Geez, that seems like a boy. That's what your shift is. How come? Oh, the engineering standard turned out to be exactly 8 hours. That's amazing. You know, on this 48-hour one, I just challenged them and said, "Can we do it in 47?" They said, "Yeah." How about 46 hours? Yeah, it should be okay. All right, I'm going to keep going until you tell me to stop, guys. Well, they didn't know. And again, when they went and did the study, they found out that it only needed to be 20 minutes of curing time. All right. So challenge everything. Okay. This is right from Toyota. It's right off their website. A standard in process, work in process stock is the amount of material that is flowing through a process when work is proceeding smoothly. It is the minimum amount of material needed to maintain a smooth flow of production without accumulating inventories. Got that? I mean, that's right out of the mouth of Babe, if you will. Okay? Right out of the mouth of Babe. And some of the ways we calculate, I won't get into too much detail here, but if you're using a curtain quantity where you have an outside process where the product has to leave and come back, you need inventory at that station. And you can see that right over here. You can see my arrow. So that I've got product after operation one that's going to go out, but I got product already coming back from the operation that needs to come in. Okay. Again, I want this operator to go from 1 to 3 without having to wait for the outside process. So I'm going to build a standard work in process inventory here. And if I calculate this total inventory to be 50 units, then I'm going to initially start with 0 here and 50 here in the inbox. When I do my first cycle, one will go there. I'll take one out. Now I'll have a ratio of 49 to 1. Do my work sequence. Okay. And the same thing again. One out. Now I got 2 here. Take one out. I got 48. So anyway, that's the curtain effect as we look at this. I'll let you read about pitch. I'm not going to get into that right now too deeply. But pitch is the amount of time the water spider has to come back to replenish the inventory. And that's based on takt time. Okay. All right. There's 3 types of cycle time. The operator cycle time is the amount of time the operator takes to complete one work sequence. There's a machine cycle time, the amount of time it takes for the machine to cycle for one unit. And there is the processing cycle time, which means your machine cycle time plus your load and unload of that equipment. All right. So that's the three. Now, everybody seems to confuse this with takt time, and it's not. Okay. It is not takt time, it is cycle time. And all these cycle times have to be in context, within context of the takt time. A way to look at it, okay, if the operator takes 60 seconds, operator one takes 60 seconds, okay, the cycle time of the first operator is 60 seconds. That has to be in under takt time. And you want to bring it as close to takt time as possible. Okay? The cycle time of the machine would basically be when the operator starts the machine, the time the machine takes to cycle, and when it comes to a stop. That's the cycle time of the machine. The cycle time of the process is that machine cycle time I just talked about, plus the operator unload and load time. Okay? That's key. Load and unload, because, hey, look, when I'm unloading a machine and when I'm loading a machine, it's not running. So I have to count for that time as it relates to its overall processing time. And then I compare that to takt time. Okay? So, anyway, that's what we're talking about here. Maybe a different way to look at it. You got the cycle time of the operator, not all the cycle time of the operator, just the load unload in this case, in my example, is going to be part of the cycle time of the process combined with the cycle time of the machine. Okay. So that is what we're talking about when we talk about cycle time of the process. These happen to be the documentation that we use as 5 forms. In the middle, well, let's start with the one on the left. You've got your time observation sheet where you're actually observing an actual operator for a particular work sequence. All right. And you come up with the time for that operator. The, the processing capacity form down here is measuring your equipment in your machines. This form in the middle is a combination sheet where we combine both the operator and the machine processing time to figure out whether or not we have an issue relative to takt time. And you can say I have takt time here written in red, all right, and all the relative times for the machine, which is the dashed line, and the dark line, which is a manual cycle time, and that squiggly line, which is the walk time. Okay, this standard worksheet is a visual uh, picture of what the work sequence look like. Now look at this one. There's an awful lot of walk time for this operator. Let's go from 7 all the way back to 1. Remember last time I showed you that the operators are going side by side? Okay. Not in this case. And that's very inefficient. That's what these things do. They point out all the inefficiencies. But remember, we hold the standard based on what we observe. We don't just make this stuff up out of some book. We actually see the operator do it. And quite frankly, I like to see the operator do the times themselves. Okay. Not engineers. But we're not always going to hit the standard enough because we got issues, we got problems. Well, that's when we actually do Kaizen to get rid of those problems on a priority basis. Okay. This last chart down below is how we show the operator cycle time to takt time. And you can see we got plenty of people under takt time, and we only have 2 that are over. Well, if my takt time's 60 and these operators are running at what, 70, 80 seconds, I am not going to get a part off every 60 seconds. It's as simple as that, regardless of the fact that all these other people are below takt time. Matter of fact, they're going to be waiting. Look at operator 5. Okay. Operator 4 takes 100 in, I'm sorry, takes close to 80 seconds. This operator number 5 only takes 40. Guess what? He's going to be waiting that difference for the part to come back to them. Okay. Okay. I won't get into a lot of gory detail here as to how to look at this. Suffice it to say, though, we want the operators to be involved in this and let them lay out the work sequences, and let them take their own times. Okay. So this is a time observation form where we actually calculate the actual operator cycle time. And again, right out of the horse's mouth here, Taiichi Ohno says standards should not be forced down from above, but rather set by the production workers themselves. How many people do that? How many people actually have their own production workers set the standards? Okay. All right. What we're talking about here is we do not want to have continual Kaizen. We have to stabilize through standardization and see our deltas to that standard and then prioritize those issues, whether it's machine downtime, supplier availability, quality issues, whatever. Why are we missing our standard? That is the essence of standard work. It's a tool for continuous improvement. It is not a tool to try to emulate all your waste. A lot of people want to put waste in. Hey, by the way, the machine shuts down every 10 parts. So for every 10 parts, it shuts down for 20 minutes. We should build in 2 minutes of cycle time into our standard work. No, I don't want to hide that. I want to have it come out as a delta, as a deviation, so we can prioritize improvements. Okay. I showed this slide, I think, in one of my other presentations, but many good companies, Fujio Cho, ex-chairman of Toyota, tried to practice Kaizen and use the various tools. They have to have all the elements work together in a system. You can't cherry pick tools and just put the things in that you want to put in. Okay. You can practice every day. Remember, I told you that standard work is not a noun, it's a verb. Well, here you go. Okay. Know normal from abnormal and know it right now. That's where your visual management comes in. Okay. And this is the cycle of improvement. Okay. So think about, you got your standard up on top, you detect abnormalities, you go to root cause analysis and Kaizen and change the standard to get you back to where you need to be. Now, I like to look at daily management on the hard side and the soft side. A lot of times we collect all the data, we put up all these Gemba boards, but nothing's really going on relative to responsibilities in terms of our value stream manager, our operators, our team leaders, supervisors, whoever, right? We have to have those meld together in concert. They have to be integrated. Otherwise, all you're doing is a bunch of work and you'll be fighting the same demons time and time again as you move forward. All right. So here's the cycle. And again, we want to visually detect abnormalities, by the way, not just get a report a week later. We want to know about like right now. So how do we do that? Okay. And then the process capacity analysis shows you where you have your capacity problems. It's taking the cycle time of the machine plus a load unload. We do amortized tooling if necessary. By the way, I didn't bring that up. It's too detailed right now for the purpose of this slide, this presentation. But when you look at this, you see that I need to make, I've got a capacity problem. Okay. I could only make 303 and my daily demand is 350, in which I'm calculating my takt time at. So now I have to do a couple things. Do I do machine Kaizen or do I just get out my checkbook? Do I just get out my checkbook and say, hey, I'm going to buy a new machine? A lot of companies do that. That's not what we want to do here. I rewrote the capital appropriations request, and I talk about this in lean accounting, where you have to first tell me why you need a machine, what Kaizen you did on the old equipment, and a bunch of other questions like what's the takt time? Is this a battleship or a PT boat? I don't want to buy a big machine that does 50 different operations at once. I'll just create a takt time problem. Okay. And this actually happened to me. We had a client who had a cell. And again, I'm going to make up the numbers because I don't remember what they were exactly, but you'll get the idea. It's very representative. 5 machines, let's say takt time was 2 minutes, 5 machines, all of them met takt time. Okay. And let's just argue that every machine had a 2 minute cycle processing capacity. So everybody met takt time, no problem. So this total processing capacity was 2 times 5, 10 seconds, 10 minutes. Now, they went and bought this big behemoth machine where they combined all these operations into one machine, and the total amount of time was 7 minutes. Processing capacity, 7 minutes. So I got there and I saw this thing and I said, "Oh my God!" They bought a battleship, and the client said, "Hey, Mark, we saved 3 minutes of processing time on this machine." And I looked at him and I said, "Well, did your demand change?" "No, it's the same demand." "Okay, well, how's your second and third shift doing?" "How'd you know we had to work a second and third shift now?" "Because you just violated your takt time. If your takt time's still 2 minutes, and this one machine now does it in 7 minutes, you're over takt time." Okay. I mean, back in the old system, we had a one piece flow cell, and every machine was producing at 2 minutes. And we are able to meet demand on one shift. You now put yourself on a second shift because you're doing the math wrong. You're thinking about this wrong. So be careful on that. So I would always challenge people on their capital appropriation requests as to what's the takt time, what's the CPK, what's the changeover time. Look, equipment manufacturers do not want you to buy, they want you to buy the next increment of capital. Okay. Now, through the 3P and moonshine process that we work on here, we will actually design equipment to be in context with all these principles. And then nobody in your industry can touch you when you do that. All right. Okay. This is where we bring in the combination sheets where we actually bring in the operator and the machinery into one form. And we look at it together. Now, in this case, my total cycle time, including uh, for the operator, is 71 seconds, it looks like. And my takt time is being 77. Well, I'm within the context of takt time, aren't I? But let's say I have a problem on one of these. Let's say a load unload gets stuck or something, right? How do I account for that? That might put me over takt time. Well, if as I start looking at all these problems and I can't hold to this standard, I prioritize those into Kaizen events. That's what standard work is used for. Again, it's not to document every little thing you do. Standard work is used for continuous improvement, right? Standard worksheet, again, you probably saw that earlier where you're showing the flow of the operator. Okay. And a question you might ask on this one is why do we have this operator going all the way back to one from the back of the cell? Once the operator gets done with number 7, he has to go all the way back to the beginning of the cell. That's all waste. And these tools are designed to help you see that. Okay. I told this story already earlier about, the cow saying, Deluzio, son, you don't know standard work. And again, lesson learned, and just, you know, remember that story as you go through and catch yourself. If you're not doing it, but you say you know it, you might want to catch yourself and check yourself at the door. Okay. Last chart is what we call a Yamazumi chart or front loading chart, where we initially lay out all of our operators. So you can see on the top here, we have 2 operators over takt time and everybody else seems to be under. Well, I want to redistribute all this labor back, what I call front loading, and move everybody up as close to takt time as possible, and the least operator being the last one on the end. And as I make improvements, I'm constantly shifting my labor. This is why multi-skilled operators are really important, so that everybody knows how to do at least 2 sides of them every time you come in and say, okay, you got to learn new skills, right? So that's what this is for. So we have the initial times that we've taken up on top. We don't want to balance. So many times I hear people, we have to balance the takt time. No, because as you see in that middle chart, we will overproduce. We will produce too fast in a one piece flow environment. We're going to produce too fast. We want to bring people as close to takt time as possible and have what we call a least operator. All that waiting time you see on every one of those 5 operators, A through E in the middle, we put into the least operator at the end. We want to see that visible, right? And as I take more time out through Kaizen, I will continue to redistribute and front load my cell where eventually operator E goes away and we redeploy the operator somewhere else in the factory. Okay. So that's how we make improvement here. Otherwise, if I made a bunch of improvements on A, B, C, D, and E and just brought everybody in the middle down a little bit more, I haven't done anything with my labor in terms of headcount. And I might have to hire somebody else in another part of the plant because I didn't free up operator E. Okay. So something to think about as you go with this. And then after Kaizen, when we do enough Kaizen where all the cycle time goes away, either in A, B, C, D, or E, we redistribute. We come back and we got 4 operators loaded to takt time. Okay. And the process will continue where D becomes the least operator as we go through. Okay. Keep in mind that standard work does not replace standard operating procedures or work instructions. Okay. Please do not think that's all you need. They're not detailed enough to do what this chart is doing. So we still need these kind of tools to back up the specifics of what operator is doing. Okay. And lean does not mean less employees are needed. I can tell you right now, if your company is not guaranteeing no layoffs because of lean improvements, you got a train wreck on your hands because nobody's going to sign up to make improvements if they know they're going to Kaizen themselves out of a job. It's simple math, and I can't believe how many companies have not done that. And worse yet, when there is excess, they march them out the door. Then they come to the other employees and say, "Hey guys, you want to get involved in the Kaizen team? We'd love to get your ideas." Yeah, I bet you would, right? Those operators will work against you and they'll find ways to maintain their employment and you won't even know what hit you. Okay. Okay. This is my book, Flatlined. I named this book after the words that were spoken to me when CEOs would call and say, "Hey, Mark, we've been doing lean for 5 or 10 years and we flatlined." I heard that word so often as I looked at all these different industries over the course of 3 decades in 5 continents and over 3 million miles in a metal tube. I found there's some very common reasons why people flatline, and it doesn't matter the industry. Fracking, logging, oil and gas, pharmaceutical, any kind of manufacturing, defense, medical devices, insurance, financial services, it doesn't matter. Construction. These reasons I see as a common thread as to why companies flatline. Okay. So there's my contact information. You can get my book on Amazon.com. My contact information is right there. If you have to call me, email me with a question, would love to talk to you. Okay. So this was standard work, and I do appreciate your time. And hopefully we'll see you next time. Thanks. Bye bye.